Hello everybody, my name is Mehrdad Hajizadeh and I'm a researcher at Technical University of Chemnitz, Germany. I'm pleased to present our collaborative work, DeepRed, a deep learning power command and control framework for multi-stage red teaming against machine learning-based network intrusion detection system, conducted together with colleagues from these universities. Let me begin with a quote from the old Chinese book, The Art of War. To know your enemy, you must become your enemy. In cybersecurity, defenders have many tools to detect and mitigate attacks. But tools alone aren't enough. They need to be tested, of course, not by the real criminal, but by the red teamer who simulates real attacker behavior. In this work, we are trying to think and act like real attackers to expose the vulnerabilities of the targeted ML model. So let's think like an adversary and see how can we compromise a system. Here we are having different tools like command and control, reconnaissance, and phishing to launch the attack. As you can see, there are many ways to get initial access to the host. Okay, so what is next? Of course, we don't gonna stop here because we love lateral movement to penetrate more, or maybe compromising more machines for DDoS attack. We can steal the data or deploy a ransomware to shut down the whole factory. Now, the question is, what is common in all those attack stages? They all require network connectivity. That is why network intrusion detection systems are critical. They continuously monitor network traffic to detect malicious activities and make alerts. There are two main categories: signature-based, which detects known attacks but struggle with the new attacks; anomaly-based, like those using machine learning, which can spot unknown or complex threats. With the success of AI in detecting malicious activities, the attacker goals shift to break the AI-powered system. Adversarial machine learning, or AML, investigating attack vectors regarding AI system and try to provide defense mechanism. Considering common security measure, confidentiality, integrity, and availability, the attacker could poison the training data, affecting the model performance, or can launch resource exhaustion attacks where they intentionally send input that increase latency or energy usage. They could steal the model or craft adversarial example to cause misclassification or evasion on the targeted ML model. We focus on these two. If it is a decision function, the defender wants to minimize the error, but of course the attacker wants to maximize the mistake by perturbing the input data. In the rest of the presentation, we are looking for delta, the perturbation value that leads to evasion. Now let's think about ML-NIDS. Imagine we want to carry out an evasion attack by perturbing the input data. In domain like computer vision, attacker can freely modify pixel value to cause misclassification with few limitations. However, network traffic is highly constrained domain, and input must be comply with protocol specifications like TCP/IP. Even after valid perturbation, how can we ensure the attack still performs its original harmful function? This is where we found a huge gap between academia and the practice. And the threat model, which I will discuss about it in the next. Let's look at why threat modeling is important. Say a machine is infected and is talking to C2 server. Meanwhile, a copy of the traffic goes to ML-NIDS. The model sees the statistical flow feature for detection. Now, the threat model consists different parameters and assumptions to define attack vectors. For example, is the attacker is insider or outsider? Do they know about the features, the model, the pipeline? Are they attacking the feature space or the problem space? So it is not just about the white parts or black parts. We need to think more broadly to model real-world adversarial attacks. From the threat modeling point of view, most research focus on the feature space, like changing flow feature to bypass detection. But real-world scenario, attackers usually don't have that kind of access since security devices are kept in a highly restricted environment. When the focus is limited to the feature space only, the problem of adversarial robustness is often reduced to simply generating examples that cause just misclassification. So overlooking critical aspects such as intent and the network traffic characteristic after perturbation. Also, it is questionable if the attacker really has capability of modifying feature values right before feeding the ML pipeline, or regarding domain space. As shown in this slide, the ML model only sees extracted statistical feature in the feature space. It is essentially disconnected from the problem space, where the actual raw network traffic and malicious behavior exists. Or about attack functionality preservation. Let's say the attacker goal is data exfiltration, which is happening in the problem space. So the main question is that how can we be ensure that adversarial example in the feature space alone still behave like a real malware and still achieve their goal? Therefore, to evaluate the adversarial robustness of machine learning-based network intrusion detection system, we take an offensive security approach through a multi-stage red teaming. We use MITRE ATT&CK framework to define high-level cybersecurity goals and map tactics, techniques, and procedures needed to achieve them. Then we extend with AI red teaming using MITRE ATLAS framework, which focus on identifying weaknesses in AI system. MITRE ATLAS include AI-specific TTPs like reconnaissance, resource development, AI attack staging, and defense evasion. This way, we cover both cybersecurity and AI attack surfaces that enables full spectrum coverage. Let's begin the first red teaming step by defining high-level cybersecurity objective. C2 is one of the most critical tools used by various criminal groups. In this work, our goal is to establish a stealthy communication channel with compromised hosts, with the capability of performing command execution and data exfiltration. After defining high-level attacker goal, let's look at the overall steps required to achieve them. We assume the attacker strategy in three main phases, starting with model stealing, where the attacker builds a substitute model to avoid high interaction with the actual system. Next, generating adversarial example in feature space to identify the delta. Finally, once we found the evasive perturbation values, we need to realize them in the problem space to establish the stealthy C2 channel. So let's begin the attack together. In the reconnaissance stage, the goal is to gather information about the targeted AI system, such as training data, model architecture, or features. This can be passive by using open source intelligence data like scientific paper about the target AI system and organization documentation, or it can be active that requires interaction to the target. After reconnaissance, the next phase is resource development, where we build the tools and data needed to support the attack. In our case, we need benign and malicious traffic data for different steps in generating adversarial example. To do this, we develop software agents for collecting benign traffic mimicking real user behavior, like browsing top Alexa websites, forums, social media, and many more. On the malicious side, as you can see, we use real-world C2 framework to simulate attacker behavior and generate various attack traffic. And I'm pleased to share that we've released this dataset publicly. It's so-called Technical University of Chemnitz Red Team 30, and it includes 30 different cybersecurity red teaming scenario for ML-NIDS benchmarking. So far, we've done reconnaissance and development, the tools and the data we need. Now we are in AI attack staging, including different techniques, starting by launching model stealing attack to build a proxy or substitute model that mimic the behavior of the target model called Oracle. We do that by querying the Oracle, collecting its output, and using them to train a local model, so we can continue operation offline. To evaluate the performance of the substitute model, we measure the agreement score between the target model, Oracle, trained on random forest or KNN, and the substitute model, but using different query budgets ranging from 100 to 500. We tested on TUC Red Team 30 dataset and also on the CIC IDS 2017 dataset using clean correct version, since the original had some issues. As you can see, the overall performance of the substitute model was strong. As the query budget increased, both agreement score and AUROC get above 98%, showing that the substitute model could closely capture the targeted model decision function. Now we have the substitute model. The next step is to craft adversarial example and try to evade it. But how can we find the evasive perturbation values, the delta, that cause the misclassification? We can do trial and error through blind random perturbation, but that's not systematic or reliable. Instead, we propose why not using the paradigm of AI against AI to automate the process of discovering blind spots in the targeted ML model. For that, we use GANs, generative adversarial network, because they are great at learning complex underlying pattern in data and can assist us to find the blind spot in the targeted ML model. Let's look at the overall steps here. For resource development stage, we have the delta and the pipeline, including adversarial feature engineering, to identify which feature to use for minimal perturbation. Here is some example, like source to destination, maximum packet size, number of packets, or bytes. Based on our adversarial feature engineering, we propose two novel attack strategies: single feature perturbation and single packet, single feature on a basis of minimal perturbation for evasion. GANs consist of two neural networks, a generator and a discriminator. In our case, we adopted GANs to follow network communication constraints. During the GAN training phase, based on gradient received from the discriminator, the generator learns how to generate perturbation to fool the discriminator. Therefore, once trained, the generator can produce perturbation that cause malicious sample to be detected as benign. But the question is that how do we know if the system is actually fooled? For that, we measure the attack success rate using the substitute model to verify if the generated adversarial examples are evasive. These plots show ASR across both datasets. For better visibility, we encoded the adversarial feature combination as F1, F2, and so on. You can find the detail in the paper. We conducted the evaluation using simple ML models, random forest, and KNN across those datasets. Random forest shows higher vulnerability with features like source to destination bind, leading to higher attack success rate in the feature space. So at this point, we identify which feature to perturb and what are those evasive values. Now we are at the very final stage of the attack, the defense evasion. Before moving forward and considering the requirement we defined earlier, let's quickly revisit the threat model that guided our approach. We set key conditions to ensure that the attack remains practical, realistic, and cover a broader range of attack vectors. Here's how we define the threat model. Attacker goal: the stealthy C2 operation to conduct the attacks like remote command execution or data exfiltration. Attacker location is outside of the network. The target model: we evaluate against several public ML-NIDS in the literature, such as flow transformer and SSL IDS, along with CNN, random forest, and KNN. For the attacker knowledge, the feature set is no access. Training data, no. Model architecture, no. And for the domain space, the problem space. Up to this point, we built a proxy model based on the feature space and successfully generated adversarial example that bypass it. Because of this, we know now which feature to manipulate and the exact value needed to achieve the evasion. One of our key contributions is the introduction of DeepRed, a C2 framework we built in Python using both HTTP and WebSocket protocols. But what does DeepRed actually do? It takes perturbation values we identified before and realizes them into the protocol compliant network traffic in the problem space. To do this, DeepRed uses techniques like packet injection and padding to embed the perturbation into actual malicious communication without breaking the connection or the original attack functionality. Now let's see how we achieve defense evasion against the targeted ML-NIDS. The perturbation values are embedded into the C2 communication, so when a statistical flow feature are extracted, those delta values are reflected and cause the evasion. We compare baseline models across three different scenarios. First, we evaluate the performance of each ML-NIDS in detecting various C2 operations without applying any perturbations. We observe AU-ROC values ranging from 89% to 96%, indicating that the target ML-NIDS maintaining a good discriminatory power under these conditions. Moreover, it's worth noting that the SSCL IDS is a pre-trained model, which have been trained only on benign traffic, differ from the one we use from our training data. However, it outperforms CNN and KNN. Next, we assess the impact of the random perturbation on detection. The random perturbation slightly affects the performance. SSCL shows resilience, but flow transformer shows the most drop. Finally, we demonstrate the effectiveness of our GAN-generated traffic in evading detection. Unlike random perturbation, the adversarial traffic crafted by DeepRed introduces significantly more challenges for the targeted ML-NIDS. It leads to a notable drop in AURAC with reduction ranging from 10% to 22%, clearly showing the impact of our approach on evasion performance. At the summary, we conducted an end-to-end multi-stage red teaming of ML-NIDS. We proposed two novel attack strategies, introduced DeepRed to bridge feature and problem spaces, and finally released the TUC Red Team 30 NIDS benchmarking dataset to support the security community advancing ML-NIDS research. So the conclusion is the comprehensive threat modeling is essential to uncovering a wide range of practical attack vectors. Preserving attack functionality is essential to validate intended malicious behavior. And because ML-NIDS vary widely, pipeline-independent evaluation is critical to ensure results are transferable across different systems. Now you can find the repository for DeepRed C2 in this link, the dataset, and my contact. Thank you so much for your attention.